Since we don't have an experiment, let me just describe what happens. For example, if you send a signal, a clean signal, at a frequency above the cutoff frequency, okay? And then you make a measurement, the sound will come and be reflected back. And what you will see is, without any losses, it comes back very cleanly and you can measure it. But if it is below the cutoff frequency, you send a sound like this and it will come back with some distortions because not all of it will be transmitting. Okay, and you can actually measure this and see the difference. One other thing to add here is we talked about Y being in infinite direction. If you have for example, a rectangular duct, now you have one more restriction in the Y direction, and the wave number now is equal to so Kz, this again, the Z direction, Kz is now let me move up here. Now you can see that there are different mode numbers corresponding to the different widths of the waveguide. Okay, and then make a note that the M larger than 0 and N larger than 0 modes propagate in oblique direction. With respect to X and Y. Okay. In other words, sound wave will be bouncing back and forth as it travels down. Okay. Okay, what happens at very low frequencies? It's a very quick answer. What happens at very low frequencies? Evanescent waves. Okay, that's one answer. We have yes, another one. Yes. That's it? No other waves? Nothing propagates at low frequencies? No? Well, see, here is what you need to remember. You're right, but partially right. Evanescent waves for higher modes. Okay, modes that have X component. But at very low frequencies, it is always real for plane wave, m equals 0. See, m equals 0, it's always real. Okay, kz is equal to k. You remember when m is equal to 0, and what that suggests is for very low frequencies, the only real wave or the mode is m0. So that's a plane wave that's going back and forth. So what we'll do now is cover sound propagation, in waveguides, below first radial resonance. By the way, we have only used these rectangular coordinates, the Cartesian coordinates. What do you think would happen if there's a circular duct? A lot of pipes are circular. Water pipes, they transmit sound. What do you think will happen? Changes the wave equation, but the same physical phenomena will also take place, except that it's not x and y, it will be in the radial direction and also torsional direction. And so you do actually have waves that will rotate, the shape will rotate, as opposed to this just in one direction you have a mode shape, in the other direction, so the net result is a combination. In this case, you have the radial, of course, and you also have the tangential shape. And under certain circumstances, they're called rotating modes, okay? That shape rotates as you propagate down the circular pipe.
We are dealing with plane waves, the rotating is important.
These are also plane waves. They're all plane waves, okay? But the pressure distribution across them are different. So it does become important. Okay, so just make a note at low frequencies. Below F01 and F10. They refer to the modal frequencies, FMN. Remember, we just did M and N modes. And so if it is below the radial frequency in either direction, okay, that means let's see, M less than 1, N less than 1. So below those frequencies, only plane waves. Okay, so let's let's say we have a sound source at a frequency omega in some sort of a waveguide that has a length L, okay? And what we want to do is just very briefly describe standing waves and losses in the waves. A new concept that will be helpful. Let's say sound pressure is, let's see, A, E to the I. Okay, X minus I omega T. Okay, now, if tube walls are rigid, and no energy loss, then the speed of sound, which is defined as ratio of the radial frequency to wavelength, and also you might remember from earlier compressibility, this is real. Okay, and also independent of space, time, meaning wave number, frequency, etc. So it's independent of all of these. But what happens if there are losses? Okay, how can there be losses? Write it down. If in this duct, and you will find this in air conditioning ducts, for example, I put acoustic tiles, okay, what's called liners, soft material. For example, this is an acoustic tile on the ceiling. It has a certain sound absorption characteristics. If you replace that, put something like this or what's on the floor, then the sound here actually would be louder and maybe even uncomfortable. Okay? So if you have liners, as sound energy is propagating, some will be absorbed. Okay? And how do you represent that? The way to represent it is wave number becomes complex. And then we represent it as 2 pi over lambda plus, okay? And this is the additional representation that we add to it. Usually, gamma is very small, so that we can still approximate wave number in the usual manner. Okay, so this is something just to keep in mind, because this is going to come in handy at some point in the future. Now let's go back to this and solve the problems again. Okay, both terminals are rigid. You have solved these problems, very similar ones. We can say if they're both rigid, we can write the sound pressure as a cosine wave, because we have del P over del X is equal to 0, both at X0 and XL. And that gives us, as we saw a moment ago, you have a question? Go ahead.
While writing the equation for velocity, the sign change white.
Which sign?
Between two terms.
Between here?
Yes.
when you take the derivative of this. When you take a derivative of this, that brings in a negative sign. Yeah, we need to remember that. Okay? Because remember, when you take it with respect to x, this is different than this one. That's where the negative comes from. Okay. Okay. This is a resonance condition, and I'll put Fn here. So what that means is if you excite just once at one of those frequencies, if there are no losses, sound will just reflect back and forth forever, theoretically, because there are always losses in the system. Okay? That's, let me see. And if that's the case, let's see now, sine, KL, cosine. This is rigid. Let me start from here. Rigid, the pressure. This would be for 1. And so on. These would be the mode shapes for pressure, and for the particle velocity. What is the particle velocity? It's a sign expression. That means at both ends it's a 0. This would be the rigid boundary conditions. Okay, what would it be for both terminals open? Okay, let's say both terminals open. Then the pressure has to be 0. It's a resilient boundary condition at both ends, and I will just, I think you know how to drive these now, and okay, if both ends are open, pressure must be 0 at each end and maximum in the center. And similarly, for the next mode, we have this. No, that's number 2 actually. Hold on. Could have done that. That's 3. And particle velocity, because the ends are open, it has the maximum value. And height. And finally, one end is rigid and the other end is open. And we have a mix for the pressure. Okay, pressure. This is maximum. And okay, can you tell which end is open and which end is closed? What? Closed or open? Closed? Pressure is 0 at what kind of end? Open end. Pressure release, right? Particle velocity is 0 at the rigid end. So both terminals open. So this is the open end, and that's the closed end because pressure is maximum. And the corresponding velocities, of course, have just the opposite. Okay. All right. Now, what I want to do now is derive the same expressions but using complex mathematics, okay? Any questions on these first? Any questions? No? Okay. I say ducts, but it's waveguides also, complex expressions. Okay, let's have a little sketch. Usually we indicate the one on the left-hand side as if it's oscillating, so it's theoretically the sound source. And we'll mark a distance at the end by D. Okay. Okay, in this derivation, I will drop, we drop e to the minus omega t just to simplify the derivations, but it's understood that it's always a harmonic motion. So the pressure field in the pipe is an amplitude A with a wave that progresses in the positive direction and another amplitude A sub minus for the pressure that's progressing in the other direction. And we describe here the relationship between A minus A plus. Since they are constants, okay, I take their ratio as just another constant. That's all it is. It's just a mathematical convenience. And when you do that, Now what we're doing here is using these arguments express the sound pressure wave just as a complex in terms of hyperbolic sound waves. Okay? You might say, why are we doing this? But it's for mathematical ease as we start using more complex results for absorption at the end, complex impedances and such. So with this now, we can continue and express the particle velocity, for instance. Okay, let me explain what the right-hand side is all about. If you take the argument in the first one, okay, and add to it and subtract from it IKL and rewrite it as minus IK L minus X. And similarly, okay, there's a reason why we want to do it this way. Okay, one of them is relevant to the left-hand side of the tube where the source is. The other one is relevant to the other side. Because one of the reasons we develop these is we will use them to make sound measurements in a tube like this to measure properties, acoustic properties of materials. It's very important to know when you're making, for example, models of a ship, models of a car, you need to know what acoustic properties of materials are. And it's not possible with our knowledge today to derive the properties from first principles. Okay? So you measure, just like steel, you measure acoustic tiles, you measure absorbing materials, etc. Okay? And so these measurements, these are preparing us for some measurements which I will describe later. Do you have a question? Oh, okay. Okay, so then similarly we can express this as in terms of the, let's see, cosine hyperbolic. Let's see, let me write down this. Yeah. Okay. Now that we have the acoustic field, okay, let's define impedances. What's an impedance? Physically, it's the resistance to forcing, okay? And it's in acoustics, it is the sound pressure divided by particle velocity. Now we have the simple expressions here. So if you divide pressure by the particle velocity, then you would have tangent hyperbolic pi. Actually, it's not, this is not the division of these, but we're expressing a general expression in complex terms where the specific acoustic impedance and some complex relationship between the two. And what I want to do is now at x equals 0, okay, equate this to this value. Okay. Now, taking the general expression and equating them, then I have tangent hyperbolic pi okay. So evaluating these, equating this expression to this one, and we have a relationship now for these general terms that I want to find out, okay, in terms of properties of the tube. It appears a bit complicated and perhaps there's no obvious reason, but they will become obvious in a few minutes. Okay, from there, continuing. And similarly, you can find a value for phi sub L in terms of the same coefficients. And the difference So finally, the relationship between constants at both ends of the tube can be expressed as so the values at x equals 0 are found from the piston velocity. Okay, from here. Those are the sub-zero values. That's where we find it from. Okay. Now, when you want to, for example, find the ratio of reflected to incident pressure wave at XL, that becomes a very simple expression as two phi L. And phi L is, we derived somewhere along the way, given. And the absolute value, of course, is what you're interested in. corresponding phase change. So from all of these, the material impedance can be expressed. Material impedance at the other end of the tube can be expressed as zeta sub L. And similarly, let's see now. I should put a note here. This is just a simple relationship you want to know. Oops. The relationship between cotangent and tangent. It's in your math handbooks, but it will come in handy. The impedance expression at the sound source area Okay. After we do, or you do some examples and go through these, it will start making more sense. But right now, one thing that we will do is utilize this for the reason that we drive down to begin with. How do we measure impedance of a material at the end of a tube? Because after all, you have basically microphones in your hands. Okay, using the microphone and maybe a sound source, you are to measure the sound pressure, acoustic impedance of these materials. So let's say measurement of zeta L, the impedance at the purpose. So what we do is first calculate the mean squared pressure at a distance L minus D. And that would be right here. Okay? At distance L minus D. That's what we want to calculate it. And that expression is that's the mean squared pressure that we want to calculate. And if we make appropriate substitutions, again, note that we have used a relationship. This is a cosine, not a hyperbolic, and we have used the simple relationship that relates okay, now we have an expression that's not complex, okay, for the mean square pressure, the real expression. Okay, while you look at that carefully, let's see how we can utilize that to make measurements. Okay. This is an expression for mean square pressure at an arbitrary point, okay, defined by x equals L minus D. So somewhere, anywhere, in fact, this gives us the mean square pressure. What is it that we're after? Let me explain just a few minutes and then take a break, and then we'll come back to it. But what is it that we're after? Remember when we had sound pressure in a tube, rigid or resilient, doesn't matter. The waves go, they're reflected back, and they set up standing waves. And what does a standing wave mean? At a particular frequency that corresponds to its resonance. Pressure, when you make a microphone measurement, let's say this is a rigid end, pressure will be maximum. As you come back, at lambda over 4, it goes to 0, and it starts increasing at another half wavelength, and so on. Okay? And that was described by, let's say, a cosine or sine wave. Okay? This is an analogous expression for the pressure field, mean square pressure field, inside a tube. It's complicated because we have some elements here that are related to this end surface, and also the gamma is related to any losses that the tube might have. What does that mean? That means now we have a general expression where the impedance at the end, or the boundary condition at the end, is neither perfectly rigid nor perfectly pressure release. It's somewhere in between, and that's called an impedance boundary. Okay? And after a few minutes break, we'll come back and see what this means, and using this, how can you obtain an impedance value by sound pressure measurements. Okay, let's take a 5-minute break.